Hello friends, welcome to lecture 7.5 where we shall discuss the concept of scaling function. In the previous 4 lectures we have focused on wavelets, but now we will introduce this complementary function called the scaling function. This will play an important role in discrete wavelet transform. In the case of continuous wavelet transform, the role is kind of limited. Nevertheless, the purpose of this lecture is to lay foundations for what we shall see as multi-resolution analysis in the context of discrete wavelet transform. So, the specific objectives of this lecture is to study the scaling function for continuous wavelet transform. As I said, there is another concept called scaling function in discrete wavelet transform as well, specifically in multi-resolution analysis, which shares a strong similarity with the one in CWT. We will look at the primary motivation for introducing this scaling function and then of course, learn the definition and look at a couple of examples. Wherever possible, we will accompany and complement the theory with interpretations. So, let us ask why we would like to introduce a scaling function. Now, we know that the continuous wavelet transform is evaluated across all scales from 0 to infinity, and in that process what we are doing is we are subjecting the signal to a bank of band pass filters with different bandwidths. As we venture into the low frequency regime, the bandwidth of this band pass filter is narrow, and as we move to high frequency regimes, the bandwidth increases. Now, it is useful to partition this scale space into 2 regimes, one corresponding to 0 to 1 and the other corresponding to 1 to infinity. Now, there is nothing so sacred about this reference point s equals 1, but initially we shall use this as a midpoint or as a reference point for the interval. Towards the end of this lecture, we shall generalize this reference point as well. The basic idea is to partition the scale space into 2 regions, one corresponding to the so called low frequency regime and the other corresponding to the high frequency regime. And the partitioning is justified because all wavelets with reference to the mother wave which are scaled with scaling parameters greater than 1 have center frequencies to the left of the center frequency of the mother wave, and all wavelets which have which are scaled such that they are compressed, that is for values of s less than 1 have center frequencies to the right of the mother wave. Therefore, it is reasonable to call the frequency regimes that the dilated wavelet span as the low frequency one and the compressed wavelets the regime span with the compressed wavelets as high frequency range. So, there are 2 viewpoints for partitioning this scale space. One is something that we have just discussed, which is from a filtering viewpoint. It is nice to partition the scale space rather than a scale space. Here we talk about the frequency space and the reference point being the center frequency itself, because s equals 1 corresponds to the center frequency of the mother wave. So, here I have a simple schematic for you on the slide where I show the partitioning. The frequencies to the left of the center frequency is constitute what is known as a low frequency range excuse me, and the frequencies to the right constitute what is known as a high frequency range. Now, what we are going to do is we are going to replace, in the process of defining the scaling function, we are going to replace this infinite set of band pass filters that I have in the low frequency range with a single low pass filter. That is the basic motivation. Why do I want to do that? Well, it is not so immediately obvious right now, but when we move to the next, when we discuss the next viewpoint, that is from a functional analysis viewpoint, and also when we discuss DWT, this partitioning will become more obvious, that is the reason for partitioning will become more obvious. At this moment let us say it improves our understanding and also improves the computation. So, what we are doing is we are saying that I am subjecting the signal to through two filters, one a low pass filter and the other is a bank of band pass filter. So, not necessarily two, but one low pass filter and a bank of band pass filters which are they are characterized by this wavelet filters. So, that is the basic idea. We are going to replace all this infinite set of band pass filters with a single low pass filter. Now, obviously, we know that signals when passed through a low pass filter produce what is known as an approximation. That is, you filter out the high frequency components, the ones that change very fast or relatively very fast from sample to sample. In other words, we are leaving out the details and only retaining the approximate part of the signal, right. So, that is the functional analysis viewpoint that we take next. In introducing the scaling function, the idea is to partition the scale space into two parts, one an approximation space and other detail space. So, that way we are able to extract two features of the two important features of the signal, one a global feature because approximations are carry the global details or variations of the signal and details carry the local variations in the signal. So, let me just draw a simple schematic for some arbitrary signal for you on the board. So, let us say I have the signal x and here it the signal consists of this global trend and let us say that it consists of this minor in amplitude, but high frequency to mid frequency fluctuations, right. So, there are these fluctuations riding on the global trend. What we are attempting to do here is to get this global trend that is underlying this signal and also get the fluctuations that are riding on top of this global trend. Now, classical filtering, when you subject x of t through a low pass filter, what it does is it completely loses out the details and only gives you the global trend. So, these details are lost and you will never be able to recover x of t from the approximation. If you want to recover the approximation, the full signal from the approximation, then of course, you need this complementary information that makes up the entire signal as well. And that is the basic idea here in wavelet analysis, and in fact, that is the basic idea also in filtering signal estimation using DWT, where we not only obtain the global trend of x of t, but also retain these details. But what we are doing is we are separating them out. So, we have on one plate the approximation of x of t, on the other plate we have the details of the x of t. What I mentioned earlier from a filtering viewpoint is, as you can see, these local fluctuations are of high frequency content because they change very fast with time relative to the global one. Therefore, if I want to extract the details, then I should subject x of t through a high pass filter or a band pass filter, and if I want to extract this smooth global trend, then I have to subject x of t through a low pass filter. What is special about wavelet filters is that they constitute both the low pass, band pass and the high pass filters, and you do not lose out anything until you manually throw out the particular components. You can always use or retain or throw away parts of the filtered signal components depending on what information you have priori, but you are in a position always to recover x of t from the filtered components, unlike in the traditional filters. So, the purpose of introducing the scaling function is therefore to think of passing x of t through a low pass filter and a bunch of band pass filters, or through to construct an approximation plus details at finer scales, right. So, the other point that you should remember is approximations are always at a coarser scale, because you keep throwing away every other point. For example, a very crude approximation is to throw away every other point, or every even 3 points, 2 points and so on, and what you will be left with a very crude approximation of x of t. Therefore, approximations are always at coarser scale and details are relatively at finer scales, that is relative to the approximation, and that is what you see in the figure as well. So, the approximation space is spanned by scales greater than 1, that is at coarser scales, and details space are spanned by wavelets at finer scales right, relative to approximation, of course. So, that is the basic idea and the basic purpose of introducing a scaling function. Now, the question is, how do we do this mathematically? So, we have hopefully understood why we want this scaling function. Now, before we move to the math, in both the viewpoints, whether it is the approximation or the functional analysis viewpoint or the filtering viewpoint, observe what we are doing. In the case of from a filtering perspective, what we are doing is we are replacing a bunch of band pass filters with a single low pass filter. From a functional analysis viewpoint, we are replacing the entire set of wavelets that are at scales greater than 1 with a single scaling function. Now, at this moment it may seem a bit intriguing as to how it is possible to do that and under what conditions really it is possible to do that. So, let us now turn to math for help on that. For this, what we do is we start with the recovery expression or the inverse continuous wavelet transform expression, assuming that we are using a wavelet that is admissible. In other words, the C psi exists, it is of finite value and non-zero. So, what I have done here in equation 1 is I have separated the inverse continuous wavelet transform expression into two parts, one corresponding to scales between 0 and 1 and the other corresponding to all scales greater than 1. As I had mentioned earlier, this partitioning with reference to 1 is only as of now. You can generalize this idea and you can partition with respect to any reference point, it need not be 1. So, when I do this, of course, the expressions are fairly straightforward, they look the integrands look identical here, but what do we want to do? We want to introduce a scaling function phi of t, so that I can rewrite equation 1 as equation 2, all right. So, what is the difference between equation 1 and 2? Of course, the first term looks identical, that is I have not touched anything as far as the scales between 0 and 1 are concerned, but what I have done here is I have replaced this integral in the second term with a simple convolution. The integral in the second term is the integral of a convolution, but here we have thrown away the integral and instead introduced a scaling function. And what is the role of the scaling function? Well, first it constructs an approximation, pretty much like how wavelets construct the detail. According to our notation, wavelets produce the coefficients t at each scale, and here the scaling function which is introduced at scale 1. So, we say now our scaling function is at scale 1 because our partitioning point is 1. It introduces an approximation denoted by L, L standing for low pass filtering. Both L and T are functions of translation parameter and scale, but because we have replaced this entire set of scales greater than 1, that is the coarser scales, with a single function evaluated at existing at scale 1, L here is being evaluated at scale 1. This dot here essentially means it is a dummy variable, it is the place or the position for the dot is a translation parameter. So, what we are saying here is this integral 1 to infinity convolution of t with the scaled wavelet ds by s square is going to be now L convolved with phi at that scale, which is at scale 1, and that is about it, and then of course 1 over C psi remains. Now, what we want to ask is, when is this possible? Can I replace this entire set of coefficients that I have, wavelet coefficients that I have, which I have generated with the use of wavelets at different scales with a single approximation. Can I do this? Well, it is possible, because what is approximation after all? It is an aggregate of all details. When I keep adding up many details, what I end up with is an approximation. So, that is the message that we are trying to convey here from in equation 2. We are saying I am going to replace all the details at coarser scales with a single approximation that is obtained by the scaling function. And the definition for L is given in 3 here. The definition for the approximation coefficient is strikingly similar to the wavelet coefficients, except that now we replace the wavelet function with the scaling function. And of course, we are evaluating this at scale 1, because our scaling function right now is at scale 1. And once again here, like in the wavelet continuous wavelet transform, the approximation coefficient at scale 1 can be written as a convolution of the signal with the scaling function reflected version. So, phi bar, like this psi bar that we introduced earlier, is a reflected version of the scaling function. I can also scale the scaling function, which we will talk about a bit later. Now, the question remains, when can I do this? When can I replace equation 1 with equation 2, particularly the second term? Mathematically, under what conditions can I do this? And obviously, from these equations and the discussion that we just had, there is a very strong connection between phi and the that is a scaling function and the wavelet. I can't choose my phi arbitrarily, right. So, let us look at now how to answer those two questions. Now, to answer those two questions, what we do is we equate the second term in equations 1 and 2. In other words, this integral here is going to be, should be identical to this convolution. That is exactly what we are saying here. So, L at scale 1, well, once again the dummy variable is a translation parameter, convolved with the scaling function should yield this integral here for all signals. When is this possible? Now, in many texts you will see the result that is given in equation 5 given straight away, but let me explain to you how to arrive at this condition in equation 5 starting from equation 4. It is fairly straightforward. We will make use of the Fourier transform here to arrive at the expression or the condition in 5. So, what we have here is Lx at scale 1 being convolved with phi at time t on the left hand side. So, what we shall do is we shall take Fourier transforms of the terms on the left and right hand side. When I take a Fourier transform of this left hand side expression, I obtain Lx at omega times, now this is a product, times phi of omega, where phi of omega is the Fourier transform of the scaling function and Lx of omega is the Fourier transform of Lx with respect to this translation parameter. Now, we also have seen earlier that Lx itself is a convolution at any dot. So, for example, I can take time t as a convolution of x with phi bar, right, evaluated at time tau. Now, here I have the Fourier transform of Lx, which means I am looking at the Fourier transform of this convolution, and once again I use the property of Fourier transform and write the convolution as the product. So, the Fourier transform of L is x of omega times phi star of omega, because phi bar here is reflected version of the scaling function, and we know reflections in time produce complex conjugates in the Fourier domain. That is it. So, I plug in this expression in the Fourier transform of the left hand side, so that this boils down to x of omega times mod of phi omega square. Now, when I look at the Fourier transform of the right hand side, then what happens is I have Fourier transform of the integral. Let us interchange the operation, the Fourier transform and the integral, because Fourier transform is also an integral. So, we are going to change the order of the integrations. So, we write with respect to the right hand side I have 1 to infinity Fourier transform of the integrand. Now, the integrand is a convolution. Once again I have, by virtue of the property of Fourier transforms, I have T x of omega at a certain scale s, right, times the phi bar of the Fourier transform of the phi c psi, which is a wavelet, and then I have here as usual ds over s square. But since the wavelet is at scale s, I cannot have simply psi of omega, I should have psi of s of omega times root s, right. Hopefully, it is clear now. So, we have taken the Fourier transform of the integrand, it is a convolution, therefore, the Fourier transform of convolution is a product of T x of omega comma s. Remember, we are taking Fourier transform with respect to tau. So, it is a product of this times the Fourier transform of the scaled wave or the wavelet at scale s, and therefore, we have root s times psi of s omega. Once again, recall that this continuous wavelet transform is nothing but a convolution of the signal with a reflected version of the wavelet. Therefore, I have here, let me write that for you. So, T x here, T x of omega comma s is nothing but x of omega times root s times psi star of s omega, because it is a convolution of x of the T x of tau comma s is a convolution of x with the wavelet at that scale. Therefore, we have this situation here, because of the reflection I have a complex conjugate, and when I multiply both this I end up with this integral here, and let me write that here. Therefore, this x of omega times phi of omega mod square is integral 1 to infinity psi of s omega mod square by s times ds, and that is exactly times x of omega, sorry. Now, what happens is, since x of omega is independent of s, it falls out of the integral, and therefore, what we are left with is a relation that you see in equation 5. That is how you arrive at this expression, it is not out of the blue that it comes about. Now, with a change of variable, you can arrive at the final integral that we have here as omega to infinity. All you do is you replace s omega with the corresponding variable here z, and then you should be able to come up with this integral. That is a fairly straightforward expression. So, hopefully, now you understand the conditions under which the identity exists, that is, under which we can replace a second integral in equation 1 with the one in equation 2. More importantly, the conditions under which I can find a single scaling function that takes the role of infinite band pass filters or the infinite wavelets, number of wavelets at scales greater than 1, right. Now, what we can see clearly here is that the condition is not really imposing anything on the phase of the phi, it is only imposing a condition on the magnitude or the squared magnitude of the Fourier transform of the scaling function. Now, because the scaling function here is playing a complementary role to that of the wavelet function, the scaling function is often called the father scale or the father wave, and the mother wave of course is the c of psi of t, right. Now, if I know for a particular wavelet, I can also always derive the scaling function. Of course, this integral here that you see, that is omega to infinity psi of z mod square by z dz. This integral is familiar to us in the form of admissibility constants. When you recall that the admissibility constant has a similar looking integral, except that the limits run from 0 to infinity, right, and we will talk about that soon, and in fact that places a requirement on when the scaling function can exist, right. Okay. So, the scaling function is decided automatically by the wavelet, but there exists some freedom, and that freedom is in the choice of phase for the scaling function.